given that our course is multivariable calculus and it has the word calculus on the tin, we better find some calculus when we open it up. And today we're finally going to get some calculus going on. And so what we want to do, now that we have some familiarity with how parameterized curves, vector valued functions can parameterize curves in 2 space, 3 space, n space, the question would be, what can the derivatives of those vector valued functions tell us about those parameterized curves? So in our earlier examples, we saw, for example, this parameterization of the unit circle where it looked like, we wanted to be able to say something like, well, this is a parameterization of the unit circle that looks like it kind of starts out slow, maybe. It's not covering a whole lot of ground in the beginning over equal intervals of t, but the further along that we go, the more ground we're covering during each interval of t. And so we'd like to say something like, this parameterized curve starts kind of slow and then it speeds up. So we want to have some notion of the speed of a parameterization. That feels like the kind of thing that should be related to a derivative. After all, velocity is a derivative of a position function, right? So if my parameterized curve is describing the location of something over time, then its time derivative is probably related in some way to describing the speed, how quickly that thing is moving. And if we can talk about derivatives, it means we should also be able to talk about tangent lines. After all, in single variable calculus, that was the meaning of the derivative. The original geometric meaning of the derivative is the slope of a tangent line to the graph of our function. Well, in 3 dimensions, it's complicated to talk about slope. We can't really do it using a single number the way that we could in 2 dimensions. But is there a way for us to use vectors to talk about the directionality of a tangent line? Could we find a parametric equation for a tangent line using our understanding of how to find parametric equations for a line? And if we can talk about velocity, we can also talk about its derivative, which is acceleration. So if we want to do physics, once again, we could do kinematics problems. If I have a force acting upon me, that force is going to give rise to an acceleration, according to Newton's second law. And then if I know the acceleration that my body is being subject to, then antiderivatives of that acceleration can then tell me what my position ought to be. And that is kind of, that's a whole semester of classical mechanics in a nutshell, is kind of that set of observations. So this is what we want to use the calculus of vector valued functions to be able to do. So let's start out. The first preview activity for this section just sort of invites you to do a calculation of the derivative of the vector valued function whose x component is cosine of t and whose y component is the sine of 2t. So what I want to do actually is get us into this preview activity and once again equip you with a Desmos worksheet to actually do the visualization portion of what we're doing here. So let me real quickly just make an adjustment to this worksheet and then paste a link in the chat for you. So it's cosine of t is the x coordinate and sine of 2t is the y coordinate. And I'm also going to give you, well, let me turn these off. So I just want to hide a few things on this worksheet that I not quite ready for yet. And then I'll paste what I have into the chat for you to play around with as you work through the preview activity in this section. So when you found the derivative of this, so you took the derivative component by component, right? So the derivative of cosine t was minus sine of t. The derivative of sine of 2t was twice the cosine of 2t. Again, don't forget that chain rule. And then when you evaluated that at t equals pi and plotted that vector with its initial point at the place where the parameterization is at pi, you got this vector that pointed sort of vertically upward. So if we look at what the derivative vectors look like sort of everywhere along my parameterization, sort of what's your observation about what these derivatives are telling us about this parametric curve? Like, what kind of a relationship do these derivative vectors have to the curve?
Tangent?
They certainly look like they're tangent. Yeah.
Hmm.
And so one of the first things that leads me to think is we could, if we wanted to, use a tangent, use one of these vectors as the direction vector of a tangent line to one of these parametrized curves. So that kind of gives us the first use case for what we can do with the derivative of a vector valued function. The derivative gives us a tangent vector to the parameterized curve. And that's kind of what this activity number 2 walks through, but I wanted us not to get sort of bogged down into those details. But that derivative gives us a tangent vector. And then the next section sort of justifies why it is that we can take derivatives one component by one component. Again, sort of treating I, j, and k as though they are constant vectors, and then just using the fact that the derivative of a sum is the sum of the derivatives. So if and when you're feeling like you want a good review of some derivatives from calculus, you can work through activity number 3 in this section, which just invites you to take derivatives of these vector valued functions, which is just taking the derivative one component at a time. So that's where our study of derivatives kind of begins.